you guys?
Hello. Fine, fine. You too?
Yeah, I'm doing quite well.
Right.
How's everyone?
Cool. Is everything set up, Michael?
Yeah. Everything is working.
We're streaming
Yeah,
on Twitch.
yes, of course. We are. I still have to open up the chat in browser, but aside from that, I only need the waypoint to travel to. Oh, and the online command.
Good. Yeah, it seems that we may have some technical hiccups with our connection. I believe that we are so far away from civilized space at this point that the signal is a bit weak. So if you guys hear any artifacts, or you think that you'll stop hearing us for any reason, just drop a line in the chat and we'll see what we can do. Now, that being said, I would like to apologize for not having a show last week. Sadly, both me and Dr. Shoba, we were quite busy.
Mostly me. Hello.
Mostly her. I was going to introduce you in a bit with a catchphrase, and now you ruined my moment. Good job, Doctor.
Oh, go ahead.
Yeah, well, it's too late now. Thank you.
No,
anyway.
No, you can have the satisfaction. Go ahead.
I was going to say, this is not going to be a proper science show without our doctor, and then I would have introduced you.
Oh, sorry.
Okay, so yeah, well, it's too late now for excuses.
Well, no, just do it.
You ruined my moment. I'm sad now. I just leave it to you guys. No, I'm done.
Aww.
Okay, bye.
I was
waiting.
Episode of Dangerous Cosmology.
Yes, to be fair, I was waiting for the entire day. Okay, in the office, I was thinking about how to do this, and then you go and you ruin things.
Aww.
Good job.
That's what we do.
Everything all the time, Anyway, what a week, guys. The topic for tonight was supposed to be beyond quantum gravity. We were supposed to talk about the current cutting-edge theories and ideas and hypotheses that would explain how the universe works. So we were going to talk a bit about string theory, supersymmetry, stuff like that. We mentioned those things a few weeks ago during one of our shows, but we didn't go into details. And we thought it would be a nice thing, explain a bit more for whoever is interested. However, yesterday, something big was pre-announced, right?
Yes. A teaser was released.
A trailer of what will happen next week.
Should I do a drum roll?
Yes. Drum roll.
That's not a drum roll. I don't have. I don't have a hard service.
That's just sad. Are you just? I don't know.
Hang on.
Sounds like you're slapping your buttocks or something. Okay.
Hang on. That's. I might just make it worse, but this might work. No, that's wait.
Look,
I'm gonna give up.
We really don't need that. It's right. But anyway. Anyway, look, we appreciate you.
No, I'm sad.
Oh.
Just stop. Yeah, we're all sad.
Anyway.
I mean, I don't want to be the only one sad, okay? Because my evening was ruined by the ruined introduction, so now you have to be sad too. Anyway, so we got this pre-announcement.
Yes.
And next week, on Wednesday, just in time for our next show, what will be revealed, Doctor?
The results of the Event Horizon Telescope, finally.
And as you can infer from the name, it is a telescope that looks at event horizons, I guess.
Yes, for the first time, this telescope was designed to image the event horizon of Sagittarius A star, and it will have a big announcement, a big reveal next week.
That is...
So, very likely, the first image of a supermassive black hole, actual image, which is so cool.
This comes at a rather fortuitous time, because we recently, just a couple of weeks ago, flew past Sagittarius A star. So we have seen it already. We are way ahead of those telescope guys. Maybe we should send them some screenshots. Hey guys, we were there before you.
Yeah, and guess what? It doesn't look like that.
How do you know?
Because they already detected preliminary results about 8 or 9 months ago.
Spoilers.
Spoilers, they were
We
preliminary
don't. No. We
results.
don't want spoilers.
Spoilers,
No,
it doesn't
we don't.
look like what it looks like.
I
in the
believe
images.
in the spoiler paradox, where if you hear the end of a movie before you see it, you appreciate the events. So I say, Doctor, continue.
Yes, please spoil us.
There were, the last time they gave us an update on how it was going, basically they got far enough in their analysis of the light to say that there was something there where Sagittarius A star is supposed to be. It is emitting some light, and it's not just a blob. It is not symmetric, there is some structure to it. Something like either a disk or multiple blobs or crescents around some. So they had enough data just to say that much. There's a source there. It's not a blob.
Yeah, we will talk about it, about this in detail tonight. And as usual, we will take questions. We have quite a few of them lined up already, but we are reading the Dangerous Cosmology channel on the Distant Radio server and as well the Astronomy channel in the FleetCom server. Michael is also monitoring Twitch and YouTube, right?
We are.
Cool.
Nice.
So
That was French and
If you're-
pirate.
Arr.
if you're listening to this and you know someone, like maybe your friends or families that are not listening to this, send them the link. Because everyone needs to hear this. Because
Yes,
I'm not sure if
this
it
is
is
breaking
clear,
news.
but
This is really breaking news.
well, I mean,
I
it's
knew
not
I
like
forgot
we
something.
are. I have what?
No, me. I need to.
You.
I need to post that I am live with everyone here.
Yeah,
I have
do it.
failed you all.
Do it.
Oh, yeah. I mean, everyone needs to listen to our shows, but of course, we are not breaking the news ourselves. However, I would like to, because this happened to me. Okay, when I read the news, at first I was like, oh, okay. Then I thought about it just for a few seconds, and I went like, oh shit, because we are kind of used to the idea of black holes, not only from elite, but from popular media and movies and books. We kind of take them for granted by now. Of course, they're extreme, they're weird, scary, but it never occurred to us. Sometimes we don't even think that we actually never saw one. We know they exist because of data, because of what's around them, but it's not like a star that we can see it. We just think they exist. We believe they exist because physics checks out, but we don't really have a picture. And this is the first time in human history, and we are the first generation of humans that we'll be able to actually see a black hole.
Yeah.
And that
It's
is
exciting.
that doesn't really sound impressive, but when you stop and think about it, it does. It is. I mean, yesterday when the news broke out, I was in the office and I told my colleagues, and they were like, "Oh, nice." And I was like, I was trying to explain. Yeah, do you understand what I'm talking about? Oh yeah, Sagittarius is like the constellation, right?
No.
It is not. It is the actual black hole of the. Oh, that's very far away. Yes. Okay. So, where do you go to for lunch? No, do you understand the magnitude of what we're talking about? So, it's not like aliens and everyone is going batshit insane, but this is quite revolutionary. I expect that whatever we will be shown next week, pictures, it will appear on science books, maybe even history books for ages to come.
For sure.
Yep.
So it is quite something. Now, I'm talking too much because I am overly excited. I will shut up, I swear. So the first part of the show will be about, we will just ask our doctor some questions and try to, I don't know, spoil a bit. What shall we expect from next week? And what are the possibilities? What are the hopes, maybe, of the scientific community, that what will happen? What will be the repercussions? And if we still have time, we will go back to the original topic about talking string theory, supersymmetry, and other things. If we don't have time for that, we'll keep that for next. No, not for next week, because we will have
Why
other
not?
things to talk about next week.
Well,
But,
the thing is, the press release is at 3 p.m. Central European Summer Time. So this will be 1 p.m. In-game time. So it will be quite a bit before the actual Dangerous Cosmology episode, and I plan to...
Yeah. So no. Obviously, next week we will talk about that.
We have 2 shows
So
next
we
week for
will-
everyone, if you don't
we'll
know
have-
yet.
No, well, not at 1 p.m. I won't be available at 1 p.m.
Yeah, but
I'll
I
be
Well,
organizing
be.
some will be,
I-
and
Yeah,
we
but
will be commenting it live.
yeah, sure. I think our doctor will be commenting it with, during her work hours.
Yes. So
right?
organizing an official viewing party at work.
Yeah, I'm not sure we can officially broadcast your part.
Probably can. I guess. I'll look
Really,
into
we
it.
can hear all the
we
nerds
need
screaming,
Written
Yeah.
consent. We would need written consent, but that's all.
like all the nerds screaming.
Well,
Please, God, no!
Yeah.
Oh my God, help!
Yeah. So
If
we will be
actually
doing that
go
next week. But
Well, I'll shut up.
yeah, I will shut up too. But okay, let me start the questions. Okay. First of all, what is the current mood in among your colleagues and in general among scientists? Because people like us that are not scientists, we are excited, most of us. But how about you guys? What's the feeling around? Were you expecting this? Did it catch you by surprise?
we were expecting it, maybe not so soon. So basically, the Event Horizon Telescope got a big upgrade about 9 months ago when they added one more site. Basically, the Event Horizon Telescope is this big collaboration all across the world. They have 4 main telescopes spread across 4 different continents. And they added one in Chile. And that one finally made them able to have sufficiently high resolution for their image that they would actually see the event horizon and what they're currently falling into Sagittarius A star that's emitting light. So 9 months ago, they passed that limit of having enough resolution to actually see the event horizon. So we knew from then it would take at least 6 months, but probably more 3 or 4 years until they got enough data of high resolution to make an image out of it. So maybe 9 months was on the low side of how soon we expected this. I thought personally maybe next year. It's a bit early, but we knew it was capable of it, and the preliminary results looked very impressive already.
So I don't think they have mentioned Sagittarius A in the pre-announcement.
They have not.
It is our assumption. Now, I hope we're not wrong, otherwise that's going to be embarrassing.
Well, I can tell you, it's the only target that the Event Horizon Telescope is observing, as far as I know. There's a lot of speculation in that team what other things they could observe now that they have such high resolution. But what they've been observing in the last 9 months has been Sagittarius A star.
And we know that as a fact.
It's their main science goal. They have never publicly announced they're observing anything else.
Would they keep it a secret if it's something else?
Maybe, who knows? It could be. Maybe they went on a spin-off and they imaged an exoplanet when it's actually going to be an image of an exoplanet or something equally impressive. Either way, it's resolutions and accuracy of images never seen before. It's going to be something completely new. And the most likely by far is Sagittarius A star, just because there's been all these status reports every year for 5-6 years regular status reports on it.
Well, guys,
And, it's getting there.
be ready to change your desktop wallpaper.
Yes.
Because that image is going to be the next one for a few years.
Oh my god, it's going to be so low res.
No, you said it's high definition. What are you talking about?
It's higher definition than ever achieved by mankind.
I expect 4K HDR.
Oh no.
I expect that.
Definitely.
I expect VR headset quality with auditory color response.
Do not be overhyped. It's the highest resolution ever achieved by mankind. To see something so small at this distance.
But what's the point if it's ugly?
It's going to be enough to see the thing.
No, it has to be pretty. What's the point?
You have to start one day.
No, I don't like this anymore, guys. I'm not hyped anymore.
Yeah, I mean, that's the thing about hypes.
It's going to be enough to see the thing.
Yeah, but see, what do you mean by see?
It's an image.
Okay, fine, but if it's a dot in the middle, what use?
Can you imagine the first time Galileo saw the moons around Jupiter? He was like, oh no, they're just tiny blobs, disappointing. No, moons exist around all the planets. It's a big deal. It doesn't matter if it doesn't.
Who cares? We know that Sega exists already. We don't have to prove it.
Wasn't he the one who said that's not a moon?
Yeah, but okay. It's okay. So let me just ask. Because is it like taking a picture? Is that what is happening?
It's like taking a picture with many technological tricks in between.
Right.
It's a technique called interferometry, which doesn't work the same as a phone camera. There's a lot more tech and maths going into it. It's very fun, actually, if people care for a technical explanation.
Yes.
Well, here's the thing: the way, because let's start from the basics. You can't really photograph something that doesn't emit light. Okay?
Absolutely.
Sorry?
Yeah, absolutely.
Okay. So I guess that what we are photographing is the accretion disks, assuming that there are, right? We are just capturing the photons that are
Would we not be capturing, if it's the event horizon, would we not be capturing a very distinct lack of photons?
Yes.
No, you wouldn't. Because an event horizon doesn't look different from nothing. It's just black. Most often it's not hiding anything. So you would only notice a black hole either if it's accreting matter or if it's passing in front of something and lensing the thing behind it.
Yeah,
you need one of these two events to detect it. If it's just sitting there,
no, it's a common,
right?
Yeah, the common depiction of a black hole, not in Elite, because Elite black holes are weird, but in the common depictions you have this literal black circle in a field of stars, okay? And you see the black hole because there is a place with no stars and it's perfectly circular. That's the common depiction of a black hole. Maybe you see some lensing in the edges, but in general you see this black thing among stars. However, if the background is already black, that's what you're saying, right? You don't really see any circle.
You can guess it's there if it's, for example, perturbing a companion star, or if it's changing the motions of many stars around it, like Sagittarius A star. That's how we know where it is. But you don't see it. You just deduce it's there. Something heavy and black is there.
And if I remember correctly, you had a video on YouTube where there was an animation of I think it was Sagittarius A, right? Or another.
Yeah. It's the only one for which we can do this.
Yeah, so it's not
the famous movie of the stars around Sagittarius A.
So what's the difference between that video and what we'll have next week? Don't we have Sagittarius A on camera already?
Well, we know it's there, but we're not capturing light from its immediate surroundings. We haven't seen an event horizon. So some people may still say, okay, it's something black and something very heavy. It's obviously perturbing all these stars, but is it really a black hole? Does it have an event horizon, or is it just like a big dead neutron star or something like that? Some people have made these crazy arguments.
So whatever happened next week is going to confirm
that black holes exist.
What it is. I mean, whatever it is, it will be proof.
A giant elephant.
And we'll actually see, very likely, the actual black circle of the black hole, the event horizon.
So we will see this legendary black circle among
Very
the stars.
likely. I'd say 70% likely.
Okay.
Well, I can explain why. Why 70%?
I'm sure you can, but
Please do.
I'm just trying to picture in my mind, you know, what to expect so that I will not be disappointed. I'm sure I will anyway.
It will not
But-
be very high res, but basically, the first thing about Sagittarius A star that we've known for a long time is that if you image it, the surroundings of Sagittarius A stars with X-rays or with different types of light, there is a bit of gas sort of moving around the center of the galaxy, and some of it comes quite close to Sagittarius A star. So we were hoping that maybe some gas fell in a while ago, and while the gas is falling in, it's being heated up, it's forming an accretion disk, or it's just falling as a filament or some sort of non-disk structure. But as it falls, it will be heated so much that it emits light in the form of infrared. And we were right, because we detected an infrared source exactly at the position of Sagittarius A star. And we know the position from the effect it's having on the stars around it. And when we pointed a telescope exactly at that point, there was infrared light, which is the type of light you get from heating gas. Not from a star, but from gas that's being heated by something.
Okay.
So once we knew there was actually some sort of light source there, the Event Horizon Telescope really got into high gear to image it in super high resolution and see exactly what's emitting and what the shape of the thing that's there looks like.
Okay. And you mentioned earlier that you're not just capturing light like a cell phone would. You're using this interferometer thing, right?
Yeah.
Do you know how it works?
Yes, it's something that I hope to use myself on the ALMA telescope array, which is a smaller version of it, a smaller version of the Event Horizon Telescope that has about 100 antennae. It's in the desert, it's in Chile, and it can take very high resolution images by basically taking all these antennae spread over the desert, 100 of them, and combining their light as if the entire receiving area was one big satellite, one big satellite dish, like one big telescope opening by combining all these different antennae.
Okay.
So it works on that scale. Interferometry has been tested on that scale pretty well, but the Event Horizon Telescope took it up to a whole new level. Instead of having something like 100 antennae spread in the desert over a few kilometers, the Event Horizon Telescope has 4 stations across the Earth. So it's like a telescope opening the size of the Earth, effectively. When you combine these 4 stations, all pointing at the same place, with some mathematical and technological trick, you can make it behave as one enormous telescope.
That's impressive.
Yeah. And it's taken a long time to get right.
Savage Pie is yawning.
Oh,
Yeah,
no.
bored?
I'm not bored. I have just had a long day.
Oh, sorry.
We have all. Okay.
Yeah.
You've had longer days than me. I'm just not used to them yet. I'm 17. I am moody and annoying.
Yeah, look, you can be an edgelord somewhere else. Anyway,
Don't forget to sleep.
I'll-
That's my advice to
I'll,
17-year-olds.
Yeah,
I
don't
will
forget
ask
to sleep.
I will ask you some more questions about this interferometry thing. But first, we have a question from YouTube. We don't very often get them, so I want to make sure that it is asked and not lost. Erin Wilson, who is listening to us now, is asking if there could be jets coming from Sag. I'm not sure what jets he's thinking about, but
Of course, fighting jets.
could there be anything
F-16.
coming out of Sag apart from...
So, hi, Erin.
No, I don't think those jets. I mean,
Not planes.
yeah, no.
Oh my god, if there's actual jet planes there, we'll be like, what?
If there's
Could
actual
be.
jet planes, then we'll know that.
Or like,
Well,
oh
well,
shit,
I don't know where I was going with
America got here first.
That's
The
that's
Nazis
where
were on the moon
that's-
all along.
No, that's the other end of the Bermuda Triangle.
that.
Right.
We've got a
So
direct
ships.
connection to the center of the galaxy here. right
But
on the
anyway,
planet.
jets coming
Yeah.
from Sagittarius A. Most likely not, and that's because the physics of jets work much like jets of fluids on Earth. Like if you know any fluid mechanics, if you want to get a powerful jet coming out of something, you have to compress things for a small opening. Like if you have water through a hose or through your shower head, if you want to get a jet, you need sideways compression. So you only get black hole jets if you have something like a lot of material falling into the black hole and it's surrounding it, so compressing it from the side, and then the jets come up the top and bottom, so to speak. So you compress it sideways, all this material falling in, and the jets are perpendicular. So for one thing, there's not that much matter falling in to Sagittarius A star because we have mapped the surroundings, and there's probably not that much. And secondly, jets are very powerful. They emit X-rays, gamma rays, all sorts of specific radiation that happens when you force matter to do these things. And we would have spotted such jets with the imaging we already have of the surroundings. So jets, probably not. Although Sagittarius A star did have jets in them, and that's been shown a few years ago. So above and below the Milky Way plane, there are these big symmetric bubbles on either side. They really look like like an impact, like a supernova on both the top and the bottom of the Milky Way, very far, like almost the same size as the Milky Way, but vertically. So enormous lobes, radio lobes of gas that's been shocked. And we think that's left over from the last time Sagittarius A star was active.
That's just gas, right? It's not. Is there a chance that it will be condensing into new stars?
Eventually, yes. So eventually it will cool down. So currently we can see it with its emitting radio waves. That means it's hot. But eventually it will cool down because space is cold. And once it's cooled down, it will be reattracted by gravity. It will fall back into the Milky Way and make new stars. That's the big cycle of gas.
But it hasn't happened yet.
No, it hasn't. It wasn't ejected that long ago. So we think Sagittarius A star was last active as a quasar a few billion years ago.
Because I was thinking, it just occurred to me that in Elite we have above and below the galactic plane rings, I believe, of neutron stars, right? Like there is a higher concentration of specific types of star above and below Sagittarius A. So I'm not sure if that is related, if those stars were formed due to something that Sag A did to the top and bottom, no?
No, that's from a different reason, actually. The reason you have more neutron stars above and below the plane is basically when neutron stars form from a supernova, at the moment of their birth, they get a kick in a random direction. So when the star dies, they get kicked into more strange orbits, and more strange orbits means they don't have to stay in the disk for very long. They're more free to travel into the above and below of the Milky Way disk. While normal stars don't get these kicks, they just pretty much stay close to where they were born, compared to neutron stars.
Yeah, but then there should be an even concentration if it's random, right?
Well, we just know there's more neutron stars outside the disk than inside the disk. We don't know exactly if it's like in a big circle or something like that.
Okay.
We don't actually have a very good real-life map of the Milky Way.
Sorry, that was a side question. It's a bit unrelated, but
yes, Sag star and disk and jets and disks.
Yeah. Busty Wonder has a follow-up. Is the question? I'm not sure. Talk about the two polar bubbles of plasma relative to the galaxy.
Yeah, that's what I just mentioned. So it's these lobes above
sorry.
and below.
I thought it was like a follow-up, but I guess it's not. So you were talking about this technology used by the telescope. And it's kind of hard for me to... So basically what happened is you point the telescope at a specific point, in this case, Sag A, and then you collect every single photon that comes through over a long period of time. So it's not like taking a picture where you take all the photons coming out of your target at the same time, and that's how the object looks at that time.
It's not even like that. Sorry, I'm gonna stop you. It's not even like that. Taking a picture over a long amount of time is just a long exposure photograph. That's how astronomy works anyway. That's what I do. That's what astronomers do every day. For example, I want to take an image currently of a very interesting galaxy I found. I need 15 hours of exposure time. That means I'm going to take my CCD camera, I'm going to expose it 5 times 3 hours to the same part of the universe, and then I'm going to add all the photons from these 15 hours to make a picture. But that's the same as you can do with your phone camera. You just leave the exposure for a long, long time. That's how you get that's low light photography and that kind of stuff. But it's still a photo. Interferometry isn't even that. It's not even using the photons one by one and counting where they're from. It's even more complicated than that, sadly.
Okay, because, I mean, you mentioned tricks. What I would like to understand is, I mean, the data that the telescope receives, in order to become a picture that we can somewhat translate with our brain to anything meaningful, it is being quite modified in a sense. I mean, the data has been worked on and filtered or I don't know, modified in some way so that to us it looks like what we're expecting it to be, right? Where do you draw the line of what is the difference between that and, I don't know, gathering a lot of data about something and like making a simulation out of it so that we can see what the data means, which is not technically a photograph, because it's just a graphical visualization of the data.
No, there's a huge difference. Because we're still using photons, just not in the conventional way. It's still using light gathered from the object directly. It's not like we gather the light and then we make a simulation to match what we see. It's nothing like that. We get the information, except instead of receiving it by the position of the light, we receive it as the Fourier transform of the position of the light.
As the what, sorry?
The Fourier transform. Any sound processing enthusiasts out there would know what the Fourier transform is.
Yep. I can't even understand what you're saying.
None of you?
Well, it's a transformation between... you can transform waves onto an axis, some sort of... I have difficulty explaining, but I know what it is.
Yeah, right. Yeah, I have difficulty...
project it on a circle and you can just...
I know what it is.
That sounds like you did it for maths. It sounds like you did it in a maths class. You put it on a circle. And then it's on a line.
Sort of. I did it in a music course.
Yes, that's appropriate.
So you're using music techniques to find black holes.
So basically, there's different ways to record signal. Let's start with sound, because that's the one that people may be more familiar with. So if you record sound on your computer, you record it in you have any sort of music file, like an MP3 file, and then say it's not recorded in that MP3 file as exactly what. Okay, let me start again. Sound is a compression of the air, right? It's a compression of the air that changes with time. If the air vibrates really quickly, you make a high-pitched sound. If the air vibrates really slowly, it's a low-pitched sound. So what sound really is a variation of air pressure with time. But when you store it in a file, you don't literally store the value of the air pressure at some moment in time. That's not how it's encoded into your computer. Instead, it's compressed in a way that preserves the information and can be then retransformed when you want to listen to it into air vibrations by your speaker. But when it's stored, it's in a different form, a compressed form, and usually a Fourier transform. A Fourier transform, instead of telling you how much compression there is at a certain time, tells you overall what frequencies there are in your sound. So how much high pitch, how much low pitch, and how these different types of sound follow each other. So it's encoded in a symbolic way, if you want, that can be then reconstructed into actual sound.
So are you talking about how... Oh, well, my microphone, I've got a condenser microphone. I don't know about you guys, but the way that it works is it has a magnet, an electromagnet on the one side, and what you're talking about, the differences in air pressure, I'm just going to call them vibrations. my microphone picks those up, and essentially the distance from a little piece of, or well, not foil, but like I'm just going to call it foil, a bit of foil, with the differences in air pressure, that changes the distance of the foil to the magnet and therefore changes the voltage between it. That change in voltage is then stored, but it's not. If you were to store all of that, it would be too much data. And so, what are you talking about? How an MP3 file compresses that?
Yes, so it doesn't store all
Right.
the values of voltage. It transforms it into a more symbolic form, like the Fourier transform. That's the classic one. Nowadays they're more complicated, but the Fourier transform was the first one you learn about when you do sound processing.
Mm-hmm.
And that's really the same trick we apply to light. So instead of getting a photon and knowing where it comes from exactly, we measure basically the delay between when that photon hits one of the detectors and another detector. And because we have 4 detectors all around the Earth, whenever these detectors get a photon at the same time from the same source, we record basically the phase difference or the time delay between the arrival of these photons and the phase in a quantum mechanical way. So basically the delay and the difference between these different observatories around the world. So then we make a plot of what delays happen more often. So what's the most common spacing of delay between which baselines around the Earth? And once we have enough of that, it's like having a compressed file. You can then reconstruct it to know exactly how much photons came from what position of the sky. But what you actually collect over 10 or 15 years is the time delays and the differences. So it's a bit like taking a long time to download an MP3. If you only have half of it, it's not like you have half of a song. Like you don't even have the song at 50% quality. If you only stop the download halfway through, you don't have anything. Because to decompress the compressed version into something you can recognize, you need the entire thing, all the parts in the compression. And this is the same. So it's been accumulating this sort of compressed version of the image as the time delays until there's enough to reconstruct what it would be visually, if that makes sense.
Okay. Yeah, more or less.
You know, the weird
I
thing
guess.
is, that makes complete sense.
I'm glad.
No, I'm not even joking. I'm very happy about that.
Yeah, so that's basically what it's been doing, and that's why it's taken so long that even 9 months ago, even though we had like 80% of the data, we could still not transform it into the real image. They could only get as far as to say, okay, well, with this amount of 80% that we have so far, we can already say it's not just a blob, it's light that has a complex shape. Because if it was just a blob, the compressed version would definitely not look like this, and we can already tell. So they could already rule out the boring scenario where it's just a blob. But that's the best they could do. They couldn't tell which of the complex shapes it was going to be. There were still 3 main options for the shape.
Okay.
Basically.
It's like a download, but the limiter on your connection is the universe.
The size of the Earth is a limiter.
So you said though that we had some. I mean, you're confident that it is likely that the target is Sergei.
Yeah, because 9 months ago they were so close.
Exactly, and you know that we have already an idea of how it will look like, because you can say that, oh, it's not like Elite, so...
There's light, and it's not just a blob. We also know it's not completely small, so it's at least a bit extended. And basically the 3 scenarios that they say were possible 9 months ago when they published the last update, they said it could be like a crescent shape where you see the front part of the accretion disk, or maybe it's kind of to the side of the event horizon. So a black circle with a sort of crescent moon shape around it, a bit like in the movie Interstellar, if anyone's watched that. So you have this accretion disk kind of in front, like a crescent moon. Or they said it could be a full accretion disk. We actually see like an oval with a black circular hole in the middle. So you actually see the entire thing around and the black thing in the middle.
Yeah, it's gonna be cool.
Or the last option was less cool. It was just 2 blobs. Because they could rule out it was 1 blob, but it could still be 2 blobs. I mean,
Wait, so
that's the only possibility.
Sagittarius A star and B star?
Yeah, well,
Like, hey guys, it's not a blob. Hey, it's
wait,
it's actually 2 blobs. It's double blobs.
Hang on, hang senpai. If it ends up being 2 distinct blobs,
that would be so
that-
weird.
is that not evidence for a galactic collision? If there's 2 supermassive, or am I going too far there? Because we don't have 2 orbital planes or galactic planes, but
common misconception. Actually, the accretion disks around supermassive black holes are almost never aligned with the galaxy. The feeding processes are very chaotic, so they do align sometimes roughly, so that the jets actually point outside of the galaxy, but it's not like they're exactly perpendicular. They can be tilted, and actually they often are. In some cases, there's even crazy quasars where the jets actually go into the disk of the galaxy. That's been seen. And it's crazy. But
So,
yeah.
I mean, 2 blobs, you mean?
If it's 2 blobs, the most likely scenario is 2 small blobs of gas or 2 small stars that recently started falling in and they're sort of spiraling in and they haven't been distorted into an accretion disk yet.
Yeah, but we still only have 1 black hole, right?
Based on the dynamic effects on the stars around, we know the total mass and we know it's black, or at least very black.
But could it be 2 black holes orbiting each other?
And it's not like we can rule it out, but we haven't ruled it out. That's the best I can say. We don't know.
But is that
the only
something
thing we've
that
measured is the mass.
and we can't confirm that even with this picture that they took?
Oh, if there's 2, I mean, we'll see 2. I don't think it's a scenario they even considered that we could see 2 accretion disks, because that's too wild. There's too many variables. So they considered accretion disk, partial accretion disk, multiple blobs.
But could we have 2 black holes sharing the same accretion disk? Because the black holes are close together, but the accretion disk is around both of them at the same time.
Potentially, it's possible. It's possible. I mean, it's not something that they've actually modeled,
But
because
would
even modeling
that-
one accretion disk takes hundreds and hundreds of hours of supercomputer time
Oh no! I'm not
and
saying.
many resources.
I'm not
So
saying.
if you double now the amount of stuff you have to model,
I'm not
you
saying
have to
it's easy.
justify using the computers. They don't just give that time to you for free.
I'm not saying it's easy, but so the picture that we are getting a picture, right?
We're getting a picture.
Okay, so in this picture, they won't be able to say, "Oh, this is definitely 1 black hole."
Well, if we see an accretion disk,
Yeah, you just said
Yeah.
that it could be 2, though.
well, no, I mean, that would be a bit contrived. If they're very close together, then they start behaving strangely. You know, like, remember LIGO? Remember when LIGO saw a merger of black holes? That's because when black holes merge, or when they get very close together, they start vibrating space-time. And LIGO can pick that up, and we would probably know if they were in the last phases of merging, that means they were very close, there will probably be signs. So if we see 1 accretion disk, probably only 1 black hole. If we see 2 accretion disks, though, everyone will lose their minds.
Yeah.
That's good. That's good.
if we see 2 accretion disks, then I'm gonna be very happy, because I'm gonna be a smart ass about it and say, well, I thought of this a week ago.
I knew it all along.
I
what will the elite
knew
devs
all along
do?
without
Yeah,
any.
you're on record.
Ooh, what would they do? Oh, that's a topic on its own.
The devs do.
Well, that's the thing. I mean, the FDev seems to be usually quite. I'm sure many of them are actually following this news, and because they've been adding real life stuff like the TRAPPIST planets and stuff like that. So this is
They
big.
haven't added my planet yet.
They haven't?
No, my
I
planet.
thought they had.
No, there's a planet. Or well, this is my first name. It's not as I'm about to admit my first name, but no one's going to be able to track me
Ross.
down based on. Yeah,
Ross.
it's Ross. Yes, thank you. Well, there's a star called Ross 128, and there was a planet discovered around it called
yes.
Ross 128b.
I know that
That
one.
has not been added yet. And
Yeah,
I mean, it's
it's
completely
not-
illogical to be annoyed, but I am annoyed.
No, it's not like, I mean, I don't expect them to add things like this in real time, but they are quite on the ball, and they kind of know that the average player of Elite, one of the main appeals is to have the galaxy as far as we know, as close as possible as the real one.
The galaxy
With some gameplay limitations, of course, but that's part of the charm of Elite. And I fully expect them to do something about at least how Sagittarius A looks. However, I guess it's not as easy because they will need to change a lot of things.
Yes, black holes in Elite are never active, which is actually the most drastic way in which the Elite galaxy is unrealistic. If I had to pick one way, that would probably be it. Black holes are not dormant. If they're dormant, we can't spot them. The only reason we know the Great Annihilator and Sagittarius... No. The only reason we know the Great Annihilator exists is because it's eating its companion. If it was just sitting there not doing anything, we would never have noticed it. So...
It's that lazy cousin that won't get off the couch. I'm tired. I'm trying to make jokes.
I would like.
It's not a good equation.
I would like FDev to focus on black holes a bit and make them a bit more interesting. But I mean, that's another topic. But we will see, because whatever it looks like, it will change how we even think about black holes. Because maybe what we have so far painted in our minds, thanks to movies and games and whatnot, may be different than reality, right?
Yeah, I mean, I'm going to say something a bit controversial here. But the reason people are so aware of black holes as a thing is probably because of Stephen Hawking. Because he was widely regarded as the smartest man alive for decades, and that's what he spent his life working on. So of course they exist. That's how people in the public see it, I think. Even though they've never been seen in a picture before. So we have less evidence of black holes than, say, neutron stars, and yet more people are aware of them.
Yeah,
because they get a lot of attention, they're cool.
Who know about it, anyone who knew about it earlier was probably totally into astronomy and cosmology already.
Oh yeah, before Stephen Hawking, they were a niche thing. They were like an oddity of general relativity, that they were allowed. We didn't know many details about them. And even when we knew details about them, it was all very esoteric. And then Stephen Hawking came along, and people tried explaining his theories to the public. And now people know what black holes are, even though, actually, we've never seen one.
No, we have not.
There's moments where I question whether or not astrophysics is going to be the thing that I enjoy doing in my life, and it's this moment right here that makes me happy, because when I was beginning to learn about astrophysics, I looked at, I mean, at the time I didn't understand it at all, but I think when I was like, what was it, like 12-ish? I started to look at... Not too long ago, I mean, but like nearly like a third of my life. Oh yeah. Anyway, I was looking into like a little bit more of what, like, I was getting curious about how the actual mathematics and dynamics worked of like GR and SR and all that, and I didn't understand a word of it, but I saw a lot of posts that said that they predicted black holes, and so I looked into them based off of Einstein rather than Stephen Hawking, and it was after that I figured out about Stephen Hawking, and so I didn't hear about them from Stephen Hawking. So,
well, it would be a bummer if what we will see next week will disprove Stephen Hawking. Hey guys, black holes don't exist.
Well, it
Or-
wouldn't disprove
Well, then what would
Stephen
there
Hawking
be?
as much.
Sorry?
It wouldn't disprove Stephen Hawking as much. It would disprove like all of many things.
Yeah, no, of course. But I'm just
Wasn't there a
replying to what
guy
you were saying
who-
now. But
wasn't there? I can't remember exactly who it was, but it wasn't. He didn't. I don't think he did anything mathematical with it, but he predicted the idea that a star would eventually get dense enough that it would collapse upon itself. He was the guy that called it a dark star rather than a black hole. I think he was a little bit behind Einstein.
So dark stars are some of these physics fringe theories that are not quite crackpot theories, but also not quite science. They live in this strange limbo where they manage to be interesting enough that some people are ready to fund it, and they survive being pursued by one or two people for a long, long time after most of the scientists think they have been disproven. And the dark stars were one of these. So early on in GR, when black holes came along, people were arguing how to solve the GR equations. There was this branch that said, actually, all your equations are good, but it wouldn't happen in reality. In reality, what would happen if a star dies, or so they say, if a star collapses under gravitational attraction, it would never actually form a black hole. It will be forever collapsing. And as it approaches the black hole limit, it would just become more and more dense and more red in a sort of slowdown of collapse that never ends, a never-ending collapse.
to be fair, that sounds cool.
It does sound cool, but it was based on a mis-solving of the GR equations, which unfortunately survived. Well, not unfortunately, that's how science worked. It survived for a long time after most people spotted the mistake. And it's still going. I think there's still one or two guys getting funding for that.
One or two.
Yeah, I mean, that's how you know it's fringe. They can still convince some universities to fund them, but they're a vast minority.
Because they've been proven incorrect.
Pretty much like modified Newtonian gravity or MOND is another one of those. It's getting way too much attention lately. It's a bit of a powered by crackpots, even though it has been disproven pretty clearly. Overwhelmingly clearly, but there's still this one group in the UK, the only one in Europe, that are still working on it, and they have funding. They have one guy there, he has a student and a tiny team, and they're getting money to research a theory that most of the scientific community think is just not worth it anymore.
Who knows?
I mean,
maybe
You know, these things happen. It's okay. That's how science is supposed to work, right? You take the time until everyone is convinced that there's nothing to it. And eventually, I guess, like after 20, 30, 40 years, they will be convinced there's nothing there. It takes the time it takes.
Well, I mean,
Well,
technically
well-
speaking, these guys could just be being smart about it. They could just be taking the money and like using it to fund their lives and like having enough of it sent towards actually doing research where they're like, oh yeah,
No,
we don't
no.
know yet, give us more.
No, they publish proper stuff. Like, they research it properly. They write good papers. They try to find evidence. They try to test theories. And often it doesn't work. And then sometimes when it works, they blow it a bit out of proportion so that their funding continues. And yeah, that's a
I can tell immediately that
but
my
yeah,
joke.
it's fine. Just the thing that happened.
Yeah, well, I didn't get
I'm
the
gonna
joke
stop
for
trying
long. No, look, it's fine. You're young.
Oh, come on.
But so, what if everyone else is wrong and they're right?
Yeah, I mean, that's why we keep funding them. It's a long shot. It's okay to fund long shots sometimes.
Yeah, it would be
Yeah,
interesting
long shot
to
fun.
if it turned out to be true.
I mean, unless what you're saying, if they've been actually disproven, then sure. But
I mean, in the case of dark stars, it's pretty much a misunderstanding of the equations. It's like, even though physics is very rigorous, sometimes you have to make assumptions to solve your equation. and you have to kind of pick a side. Like, let's assume that this effect is negligible. Let's assume this effect is the main effect and neglect all the other effects. Because if you want to model something like a star collapse, you have to take into account way too many effects. If you wanted to do it properly, do a physical simulation, basically our supercomputers aren't capable of doing that yet. So you have to pick a few effects that you think you understand, pick the main ones that you think are going to make a difference, and then run your simulation or build a model with that. And what happened with dark stars is they neglected a whole bunch of effects that would actually allow the collapse to happen. And they focused on like a subset of things. Okay, if your very specific and obscure assumptions are correct, then yes, okay, it wouldn't be able to collapse. But we think that all these other effects are important too. So,
Okay.
How would a dark star work if it had the mass of Sagi?
that's another question. It wouldn't even be formed in a stellar collapse in that case, because it's bigger than any star we know. We know the mass by the effect on the stars, so it's not even a stellar collapse. It would be like a merger of many, many dark stars over billions, or something equally contrived.
So,
Yeah.
Yeah, going back to the actual topic, Bestie Wonder asked earlier a question that it would be fitting now, and it is whatever comes out next week as a picture or as a set of data or whatever, is that going to help you and what you do or your colleagues? Like, whatever you're researching now is, I mean, of course, from our perspective, oh, it's cool, okay, it's great, but from a professional perspective, from where you stand, is this going to help practically?
Yes. Like, so much.
Okay.
Like, so much in so many ways. It's going to be great. So the first thing is, first real test of gravitational general relativity plus fluid mechanics. So there's very few places in the universe where you can test the combination of fluid mechanics, magnetic fields, and general relativity, where all these effects are relevant at the. You have something like a star, where you can test fluid mechanics and gravity, because you have the interplay of the bubbling inside the star, and you see the surface. You can kind of predict the different layers of the star and star quakes and things like that. But it's not really general relativity, because the kind of gravitational pull that you see is not very strong. You can still get away with it by basically modifying Newtonian gravity slightly. So not a real test of GR. The tests of GR are to do with things that are very massive and the way they gravitate. And like the scale of a galaxy or a quasar, or these very high energy states. But in those cases, we don't see the fluid mechanics because we don't see the fluids. So there's been this enormous field of that's gonna GRMHD, general relativistic magnetofluid dynamics. No, I missed something. General relativistic magnetohydrofluid dynamics.
Right. Yeah, I felt. Yeah, something was missing there. I didn't tell you.
So it's when you have fluid dynamics
Yeah.
plus magnetic fields. So think of all the simulations that company makes of jet planes. You want to know how your plane is going to fly, you have to simulate the motion of the air around the wings. People run these simulations on big computers to test their products before they launch, basically. All the fluid dynamics aspects, if it's to do with air or water. And then you have the magnetic part of the simulations, things like electronics, anything that uses magnetic fields in any way, shape, or form. And then you have GR that we can only test in space in extreme conditions. But GR-MHD is all of these things happening at the same time. So it's a fluid dynamics simulation plus magnetic fields plus GR. It's a test of everything together in one. It's the most computationally intensive calculations that you can imagine. It's what even supercomputers really struggle to do in terms of complexity of the equations going on.
For now.
Well, yeah, it's at the very cutting edge of what supercomputers are starting to do. So, for example, for Sagittarius A star, the predictions of what we will see around Sagittarius A star, each of these simulated images of what it could be take weeks and weeks of running on a supercomputer, because you need to take into account all of these parts of physics at the same time in a dynamic way, and it's super
So are
hard.
these calculations that would be so difficult? Or well, I'm going to say difficult because I have a lack of proper vocabulary. But would these be calculations that would be so difficult that even Edinburgh and Harvard would be running for their money with them?
Yeah, I mean, absolutely. The supercomputers used for cosmology have often been the biggest in the world. Only recently, it's now data centers that have supercomputers bigger. So Google, etc. The ones in California, those are now the leading supercomputers. I think Harvard had one for a long time.
Are these
but
already?
traditionally,
Are these
they're
already
the biggest
quantum
now.
computers, or is D-Wave or something like that even
No,
the thing for the
No.
calculations? Not, unfortunately.
No, not yet. They're not quantum yet. So D-Wave has the first quantum computer, but it's not a supercomputer. It's super slow.
Is it feasible for those kinds of calculations?
Not yet. So currently, the best quantum computers have so little memory that they're useless. But one day they will leave the rest of computers in the dust. But that's in 20, 30 years, not tomorrow.
Hang on, doesn't Intel have like a 200 qubit processor? Or are you talking about like physical?
Yeah, but that's nothing.
RAM memory.
I mean, 200 qubit is nothing. I mean, we're talking terabytes of RAM here.
Fair enough.
It's still nowhere near in terms of quantum computing. I don't think even things like NASA or the government or China can have these things yet. Quantum computing is not there yet. It's at the proof of concept stage, where they're trying to sell it so they can have money to develop better ones. Kind of like the first computers back a long, long time ago.
I'm obviously I'm not well. What do you mean by memory in reference to a quantum computer? Because what I'm talking about is the processor chip.
Either way, so
you're getting off topic, guys.
Even way, no matter if you have 200 qubits,
I'm being ignored.
It's not gonna matter. It's way too small. Okay.
No, it's fine.
No more quantum computing.
Nah,
yes.
I mean, we can have a segment about quantum computing if you want.
So no, it's okay.
No, it's fine. I just wanted to take a question because we got another question on YouTube from Alex Conrad. He is asking if there wouldn't there be countless stars in the way blocking the view to Seg A? I guess that you can add anything, not just stars, but all sort of crap, right?
There is crap in the sense of dust and clouds of gas and just crap.
I'm glad you clarified that.
Okay.
Dust like
but
that.
there's no stars. There are no stars in the way. Actually,
more of
stars...
my jokes coming your way.
That was quite funny. It's okay. You're getting better.
I think I'm waking up.
Stars in the Milky Way don't superimpose on top of each other. Actually, a star is so small compared to the distance to the nearest, less than 0.00001% compared to the space between stars. Stars are really small compared to the spacing of stars. So actually, there is no stars in the way. And statistically, it's unlikely you would ever get two stars spaced by a lot that just happen to be in front of each other. The Milky Way is just that empty. Very empty.
Okay, that's counterintuitive though.
Well, if
you look up, well, maybe not in London, but if you go to places where there is no light pollution,
Scotland,
and you
Scotland,
Scotland,
and you look at but especially in the southern hemisphere, where you're actually looking at the center of the galaxy and at the Milky Way, the sky can get quite filled with stars, quite dense. You can see a lot of lights, and those are just the ones if you point at any direction,
Don't look at the finger. Look at the into the direction.
yeah, it does feel like you would eventually crash into a star. You know, if you just start heading into a direction at random, you will end up crashing into something just out of chance. But you're saying that it's not like that, right? It's just how it looks like.
Yeah, I mean, it's literally what it looks like, you see, because the human eye can actually only see a certain resolution. If you have something that's smaller than your smallest eye resolution, you can see it. It's just blurred. And the limit of the human eye is at about 1 arc minute in normal seeing conditions. So that means basically, if you hold a coin at the end of your arm, across from one end of the coin to the other, that's 1 degree. So you divide that into 60, and that is about the resolution that your eye can see. 1/60th of a coin if you hold it at arm's length.
What coin, though?
Roughly a coin. It's only rough.
Yeah, but what
No,
coin?
I'm an astronomer. I only do orders of magnitude.
Coins
£1
can
coin.
be different sizes. and-
£1 is what's 12 sides?
Twice the area of your thumbnail.
Hang on.
Fine, it's fine.
Don't
We
use
get
big
it.
words. It's a 12
I'm gonna try again later.
A 12 corner.
So yeah, basically, that's the resolution of your eye. So to your eye, it looks like all this light is blended, because if something is smaller than 1 arc minute, it just looks 1 arc minute anyway. It's like a big pixel to your sense of sight. But actually, the blurring due to the Earth's atmosphere, because there's a lot of that, is 60 times smaller than what the eye can see. Which is why, for astronomy, we use cameras that are way more sensitive than the resolution of the eye. Or back in the day, we used photographic plates, like big mercury plates that used to be imprinted with the light, like old-style photographs, like Polaroids. And because the resolution of that is a lot higher than what your eye can see.
So from Earth, well, not from where we live, but from like Chile or the southern hemisphere in general.
Scotland.
No, not Scotland.
Not Scotland. The best resolution in the world is in Hawaii and Chile.
Or Hawaii. So
On Mauna Kea.
you could actually say, oh, like look there, and point at a direction, and that is where Sagae is.
Yeah.
So you can say, oh, you're looking at Sagae now.
Some of the photons hitting your eye would be coming from Sagae, but your eye doesn't have the res to see
No.
it.
Of course you won't, but you know that you're looking at the center of the galaxy.
Yeah.
You can point that out.
Absolutely, it's quite obvious. It's where there's the most dust. Dust is like a cloud in the southern sky. If you ever get to see the Milky Way from the southern hemisphere, the center of the galaxy is like a big cloud across the sky.
Well, next time you guys are in Hawaii, you know what to do. Look at Sagae, while other people
are working hard.
Will be looking at the beach or basking in the sun. No, you will sleep during the day and wake up at night to look at the center of the galaxy. Because that's why people. That's why people go to Hawaii, right?
Too real. While people are on the beach in Hawaii, I was inside sleeping, waking up at 6 p.m., working until 8 a.m., and then going back to sleep for 8 hours and starting again.
Oh,
it's not a holiday. It's not a holiday.
Such a tough life. You get free trips to Hawaii, but oh, shame, you can't.
But I was a PhD student. I couldn't even afford to eat. Do you know how expensive Hawaii is? It sucked.
I would expect they would at least provide you the means to eat.
No.
A tent and a bicycle, and you're all set.
But you have to eat, especially if you're working 16 hours a day.
You could learn how to fish, I guess.
Yeah, how expensive is a tent?
Fish. Hawaii is fun.
Anyway, let me check if we have some more questions related to this.
Yeah, ask Cheng's question.
Chank. Actually,
Chank
Chank,
got a question?
there is. Yeah, there is. There's a 3-line question from Chank. Okay.
Oh, come on.
Oh, is it
Yeah,
the
it's
wall of
about-
text?
It's about lizard people or something.
No.
Okay. Let me start reading it. I haven't read it. I'm just reading it as I go. Why does preliminary data from EHT imply a universal glow rather than the expected red versus Brie orbiting the supermassive black hole at the center of the galaxy? Is it actually spinning perpendicular to the galactic plane? And not only that, one of its poles face towards us somehow. And he continues, rambling, when did the lizard people fund the super mega death weapon intent on wiping out the soul? Are we a threat? And he then continues with a call to action to those lizard people, trying to convince them to face us in honorable combat. I think he's serious. So
I am tempted to do a voiceover, but I'm tired, so it's a risk.
So, first of all, the most important part of the question, are we a threat to lizard people?
Yes.
They are extinct for a reason.
What lizard people?
Yes.
The rest of the question, I didn't even understand it, so I let you answer that.
So when material falls into a black hole, at the centermost part, when it's very close to falling to the event horizon, the heating really ramps up, and you get all sorts of weird physics happening. Like at the moment it falls in, it becomes more and more redshifted and more faint. So there would be a color gradient. It would be a very colorful process if we could see it. But two things. One is that Sagittarius A star, as far as we know, doesn't emit visible light because it's not seen in optical imaging. When the kind of light we use to monitor what the stars around it are doing, it's not seen in those images.
But we didn't
instead,
have the resolution before, didn't we? Did we?
Sorry?
We didn't have the resolution for imaging at all.
We would still see some photons coming from there in those images, like we did in infrared light, because infrared light doesn't come from stars, it comes from a heated gas. And that's what the Event Horizon Telescope is tuned to look at. They had to pick a specific frequency of light to maximize their signal. Basically, they focus on one specific frequency of light and they do that one to make sure they're not mixing different colors. So we would never see a color gradient in this image just because it's not built that way. Very likely this image will have a fake color. So sort of usually you have a yellow to red to black scale. With more yellow means there's more emission coming from that spot. So it's like a brightness map. But it's all taken in the same frequency of light, which is coming from a heated gas. That answers the first part. No color shift, because we're only looking at one specific color. And the second part of the question was about the direction of spin. That we have no idea. It could be pointing perpendicularly, it could be pointing into the galactic plane. Because of these lobes we mentioned earlier, above and below the Milky Way, we think in the past it was pointing kind of perpendicularly, but kind of tilted. It could have changed since. I mean, we think supermassive black holes may be able to kind of reorient depending on what falls into them and their magnetic fields and such. But we have no idea. Maybe we'll be able to tell from the picture which way it's oriented.
Could Sergei be a Kerr black hole?
By definition, it probably is.
Okay.
So Kerr black holes are just black holes that spin. It's very difficult to get a black hole that doesn't spin.
I always thought Kerr black holes also have the property of being a ring singularity.
A ringularity?
That's just because they spin.
A ringularity.
Yeah,
yes,
well,
exactly.
A ringularity. So Kerr
I'm
black
sorry,
holes
I need to clear my throat. I'll just be sick.
Bless you.
Yeah, bless you.
I finished my water, which was a bad idea.
What magic water was that?
Scottish water.
Is that
Aqua
Scotch?
Ardent. Aqua
No,
Vitae.
I'm serious. We're locally famous for having the clearest and healthiest water.
That is true.
And we can genuinely claim that because we don't add fluorine to it.
Yeah.
You add alcohol.
Yes. What?
Whiskey.
No. That would explain why I love it. No. That's a joke.
Is
It's a
it?
joke.
Is it?
Yes.
Anyway,
back to topic.
what?
Yes, sorry.
Uh,
That's my... Yes.
Yeah, we're mentioning Kerr black holes, right?
Yes.
So basically, if a supermassive black hole spins, it gets a ringularity. So the singularity at the center isn't necessarily a point. It can
Gets
be
a ringularity.
a ringularity.
What?
So
Is
there's
it a term that exists?
kind of. It's not sure. Okay.
I don't think that's English.
No, it's a made-up word. It's a ring-like singularity.
It's a thing.
It gets a ring-like
Come on.
singularity. So
Then
that-
I also want a cubularity then.
why not? As long as it's clear
Or
what
a
you mean.
spherularity.
I'm pretty sure I've made up words in my job.
Spherularity.
Wait, I have made up words in my job. I have had
Yeah,
to
well-
come up with words in science.
So if there is
Well,
singularity,
English
there's
is
also-
perfect.
Wait, no. This opens up a lot of options. So if there is a singularity, there's also a doublearity or a triplearity.
But that's not really
Right?
different from two singularities.
Well,
Yeah, well, it's not
No.
a singularity anymore if there's two.
yeah, it's a doublearity.
It is. Oh god.
I mean, that's definition.
Yeah, semantics.
We are going down a rabbit hole.
We should
Yeah.
we should make a show called pedantic semantics.
What? Anyway, I will not stop you again. What's this ringularity about?
So a ringularity is something that sometimes happens, maybe, in rotating supermassive black holes. It's a consequence of GR, again, but we've never seen one, obviously. And instead of having one singularity at the center, if the supermassive black hole is spinning fast enough, you get many singularities in a ring, like a continuous ring where space-time is infinitely bent, with the area at the middle of the ring being weird. Weird and impossible to reach, ever.
Aww.
So like a separate universe, in a way. Or so some sci-fi books have interpreted it as.
And Sergei is probably that.
Well, it's hard to get a supermassive black hole to form without spinning at all, right? Because it's just formed by things falling into it. It gains angular momentum, it will start to spin. We don't know exactly how fast you need to spin to get a ringularity. Maybe there's a minimum speed. That's still kind of an open question. But it's probably a Kerr black hole, because a Kerr black hole is just a black hole that's spinning. Most black holes spin.
And it is definitely spinning.
And no, it's just that by the way they're formed, it's quite hard to get one that doesn't. You would have to kind of be very delicate to make it eat stars from always a symmetric angle to not get like slightly more feeding on one side, because that would make it start spinning. You know, it would be very hard to not start spinning at some point in 10 billion years.
This is a slight tangent, but I've heard that black holes can have a charge. How does that work?
It just means they absorb more electrons than protons, for example. So if over its lifetime more electrons fall in than protons, then overall it has a negative charge.
But if nothing can escape a black hole, then how can it have a magnetic effect? Or an electric effect?
It's unclear. To be fair, we don't really know.
Ah.
So in quasars, the magnetic fields are not always provided by the black hole itself. It's really the accretion disk around it. Because a lot of quasars are very, very big accretion disks with a lot of matter being forced into jets. And that squeezing process makes magnetic fields in the structure around it, which are a lot stronger than the magnetic fields we can actually see from the black hole. So it's kind of drowned. We can measure the charge of a black hole or the magnetic fields of a black hole directly that way. So we're not sure what kind of electric fields and magnetic fields a black hole can have. In some theories, like the one Stephen Hawking was working on, they can have them. And then these fields kind of get stuck outside of the event horizon, and they behave in strange ways. As the black hole evolves, it can grow, it can squeeze, and the magnetic fields kind of get distorted over the life of the black hole, and it's a mess.
Are you talking about his idea of he said, or hang on, what am I trying to say? Give me 2 seconds.
It was probably a joke, but you failed again. No.
No, it's not. No, it's not a joke. I mean, I would have failed again, but it's not. Right. So are you talking about what he tried to describe as hairs of a black hole, or is that something else?
Sorry, is that hairs?
Yes.
Oh god, I have
as
to
in
remind
black
myself.
holes having hair.
It's
not
linked.
literally, but okay.
Not literally, but having fields sticking out of them, kind of like magnetic fields. Yeah, it's debated, and I don't know enough about both sides to really paint a clear picture. I know that there is this thing called the no-hair theorem that says that event horizons can never have fields sticking out of them. But there's ways around that by having the fields kind of close around and avoid the event horizon by curving in a certain way. It's hard GR stuff, and I'm not sure how the research is doing lately on that. It's definitely still ongoing research, how supermassive black holes can have their own magnetic fields. Although it makes sense in a conservation of charge kind of way, right? If you absorb more electrons than protons, nothing can be lost. You start with something neutral, the total charge is still preserved, or we hope.
I haven't learned anything about conservation of charge. I've only done conservation of energy and momentum. But the thing is, conservation of momentum is essentially... I was told that it's essentially just a requote of the conservation of energy, so I would assume that that is the same for charge, but then the question of how is charge linked to energy, right? So is there any difference between the conservation of charge and the conservation of energy?
Yes, there is. I'm glad you asked. That's a fun question. So in our universe, there are these things called the invariants, and we've discovered quite a long time ago that every time you have something that's invariant, that is linked to basically a physical law. There is a link between, if something is invariant, there is a rule of physical symmetry that can never be broken. So rules of symmetry and invariant quantities are intrinsically linked in a theoretical physics sense. And there are a few things that are constant in our universe and kind of define the physics of the universe by the fact they're invariant. And two of them are energy conservation and charge conservation. They are actually separate. There's a few others, like orientation. If you have an event happening, a system happening in one direction in the universe, and you take your system and you rotate it a bit, the physics will not change. So that's a conserved symmetry. And that's linked to a conserved quantity too. So basically, you have these fundamental symmetries of the universe, of which charge is one, and the conservation of energy is one, and then there are two more. There is parity symmetry. That means that if you reverse basically the direction, if you mirror your system from left to right, as if it was a mirror universe, just left, right, put a plane, reverse everything left, now is right, everything left, right, now is left. The physics are still the same, which is parity symmetry. And the last time is time reversal symmetry, which is a quantum mechanics thing that if an event can happen in one direction in time, it's also possible in the opposite direction on a microscopical level.
And
that's how theoretical physics works. In a one-sentence summary, symmetries and conserved quantities define the physics of the universe. That was a fun tangent.
I can't remember how, so I'm definitely, I am almost definitely wrong, but I heard somewhere that what was it that you said was did you say parity?
Parity symmetry.
Right. I was told that that was disproven, and that the last chance for any form of symmetry was this supersymmetry of all three of them at once, because they hadn't disproven time symmetry yet.
Yeah, something like that. So to everyone's surprise, parity symmetry is actually not true. And this goes back a long, long time. Feynman famously had this thought experiment. Imagine you're talking on the phone to an alien somewhere out there in a different universe. And you can communicate with him, you can try to understand what the laws of physics are in his universe. And you can work out, okay, his universe has basically the same rules of GR. His universe has basically the same rules of electromagnetism. Okay, so you communicate over the phone, but you can never see him. And then you try to explain to this alien what right and left mean. What's right and what's left? Can you be sure that what you call right is also what he calls right? Or could it be left? Could you just swap them? Is there any way you can disambiguate it using only a phone without actually seeing him? And philosophically, you can't. And until very recently, everyone was very sure that you could not solve this problem. There is no process in the universe that prefers being left or right. Even the rule you learn in school, if you do physics, with the Coulomb force, you have electrons going up, then you have a magnetic field going left, then the thing that you're passing a current through will come towards you. That seems like it would help you explain what's left. So you have a thing that's moving up, away from the center of gravity. If you pass a current left, then the thing will come towards you. So you do that, and if it moves towards you, that defines left. But actually, not even that, because that's the same as defining what is negative and positive, and you can't do that either. You have to be sure that the electrons that are passing through the thing are actually charged negative, and they haven't just defined it as positive. Basically, parity symmetry and charge conservation are intrinsically linked. And Feynman famously showed this.
But
that there's no solution.
So ultimately,
no,
left
wait.
and right
There
do
is a
exist,
but
but
there,
they're
right?
hang on.
Well, yeah, in Feynman's lifetime, and for until like 10 or 20 years ago, this was a fundamental rule of physics. Parity was degenerate. All rules that happen left and right can happen right to left. There was no exceptions. And then there was. Then there was this one rogue particle that for some reason, when it's emitted from an atom that looks completely symmetric, it prefers to go right.
I remember you mentioning this, that the universe, on average, prefers right.
It prefers clockwise.
Well,
The
maybe
universe,
we
for some
just
reason,
haven't
there is
taken
this
enough measurements.
one process. I know. So I just enjoy this topic.
So ultimately,
it's a fun one.
So I'm not trying to change what you said, but I'm just trying to make sure that I've got this. So what you're saying is that left and right exist, but the actual determination of which is which is arbitrary.
Yes, the universe would
Right.
be exactly the same if left become right and right became left.
But no.
And you swap electrons, positive and negative.
Wait, no.
Except then they discovered this one particle.
Yeah, so it's not the same,
not
right?
Do it. Yeah, well, it was a huge, groundbreaking, enormous result.
But it is, because there must be a reason for it, right?
Yeah, no one knows. But it really shook up theoretical physics. Parity symmetry is not true.
I mean, symmetry in general. I mean, what
Human
could be the
beings like
reason?
patterns, and so to say that the universal pattern has been broken is very difficult to understand.
No, it's not even that.
But it's so nearly true. It's a symmetry that's so nearly true, and the quantity it's linked to is so nearly conserved.
Yeah, but nearly doesn't matter, okay?
But it's still fascinating because some things are not conserved at all.
No, what I'm saying is whether it is like that nearly or by a huge amount. I mean, we all know that there's many laws of physics that if they were just slightly different, the universe would not even exist.
Yeah, no, that's a bit of a misconception.
You said that a few times.
I don't think I have.
Well, maybe not. But I'm saying that if some things were slightly different, many things would look very different. You know, just a small variation could have huge repercussions. That's what I mean. So the way I see it, it's not that surprising that something is just slightly off.
Well, there's probably something very deep there that whoever comes up with the next theory of everything, or quantum gravity, that person will see what this means and build it into a theory of the universe in general. Because
Maybe.
It's very strange and we don't really know what the hell it means.
Isn't it like the same thing that's behind the fact that for some reason there is slightly a bit, at the Big Bang, there was slightly bit more matter than antimatter.
Maybe. But
you know, it was supposed to be the same amount, but for some reason, the universe veered towards the right, and there was a bit more matter, and now we exist because of that.
Yeah, but that's not the same as the fundamental rules of physics. That just seems like uncertainty or chaos in the initial conditions. Maybe some part of the universe had antimatter, and it's just not our patch. We can only see a bit of the universe, depending on how big it is, you know? That's less deep than something you can see in a lab, where things are so nearly perfect and then they're not. It's true that physicists like order, but it's like nature's teasing physicists. Like, haha, this is very nearly conserved. You very nearly had it, but no, there's an exception.
Well, since scientists are part of nature, they are teasing themselves.
I have an analogy that I know that you will love. We are the kittens of the cosmos. Playing with cat toys of...
Meow.
Playing with... Hang on. I'm gonna try again.
Look, I'll give you an advice.
It makes sense.
No, wait. Guys.
I'm gonna start writing.
Listen. Exactly. You need to write the jokes down. Okay? Just before the show, you write them down and then you read them. You can't stop jokes midway because they don't work.
Oh.
No, I mean, it's an honest...
That was a good joke.
You didn't even finish it. How do you know it was good?
We are the kittens of the universe.
You're a scientist. I know you like bad jokes in general, but...
Hey, hang on.
What? Come on, finish what you started.
Well, no, we do like bad jokes.
Finish what you started.
I'm not a scientist yet. I can't say that.
I mean, you were going to say something, right?
No, I was going to say that. Then I stopped myself, then I said it. Then I said that I'm not a scientist yet, so I can't say that. And so paradoxically, I should have shut up.
Okay, never mind, I guess. Do we have any more questions about this? Because it's getting late. I don't think we definitely don't have time to talk about string theory now.
Sorry, we went off course, but it's
all right.
It's fine.
It's all right. I hope that the audience enjoyed this. We still have a few minutes. If you guys listening have some last-minute questions, feel free to ask. Next week, we will still be talking about this, obviously. We will have a nice little picture to look at, and we'll be commenting it with a picture in front of us. So,
what if it isn't a picture? What if we have just hyped it? What if we have gotten on the hype train for horse armor? What happens then?
What if we
I
say
don't know.
again?
I mean,
I didn't get it.
What if it's not a picture? Well, the thing is that
what if it's a song? What could it be?
No, I mean, yeah, that's the thing. When they had new, better constraints, like when they passed the point of knowing it was not just a blob, they didn't make a big press release about it. They just published it and then they hyped it in some local newspapers, you know. It was a pretty big thing. It was in some pretty big science outlets, but they didn't call a big press conference in 6 locations, coordinated and live online. The last time they announced a better constraint on what it could be. Okay,
So
there's something different this time, obviously.
So this is big.
It's big.
I mean, there is no question.
It's the first major press release of the Event Horizon telescope.
And they can't really afford not to be big at this point.
Yeah, I mean, they wouldn't have made it this big of a deal in terms of the reveal party that they've planned. I mean, they've mobilized all the journalists. I mean, 6 countries, all at the same time. I'm excited.
Oh, how marketable is this, though? I mean, what would the headlines be?
First picture of a black hole.
Yeah, but most people will be like, what's a black hole?
I'm not sure, you know.
I
mean, millions of people.
The unfortunate thing is, I get the feeling that the BBC would sort of brush over it. They would mention it on like a story on their app, and they would be like, "Yeah, sure." Because
I don't know. Like, think about LIGO, the LIGO gravitational waves reveal. People could have gone, "Oh, what's the gravitational wave? I don't care," but they didn't. It was a major society event. You know, everyone knew what the gravitational waves was after the press release because they made a big deal out of it.
I'm just saying that I don't think it will be as big as it deserves to be. That's all.
It will be. I hope it will be bigger than LIGO. I hope.
Yeah, but LIGO wasn't really that popular. You know, if you go around it, if you're already into it, but if you just walk down the street and say, "Oh, do you remember LIGO? What? Lego? Yeah, I like Lego." I mean,
I played with that when I was small.
That's the average person on the street, you know.
No, I think if you ask them, do you remember when we detected gravitational waves?
No, they would say no.
I don't know.
The average
these things
British
are proportional.
person.
It will still reach way more people than astronomy reveals ever do. I mean, our team makes press releases, right? We talk to journalists. People don't care. At least this one's like continent level, at least world level.
No, I'm not.
It's still the biggest
I
thing.
really hope that it will get the attention it deserves. That's why I really hope for a cool picture, because it's easy to sell pictures more than words, especially on newspapers or TV. You show the picture and people go, "Oh."
Remember, people got tattoos of the LIGO signal the next day after it was.
But it's not
the vibration.
Yeah, but it's not the normal thing to do. It's not common, okay?
The community of science nerds is millions big.
I just asked in my office. They thought it was about a constellation.
Yeah, I mean, of course, but it's still, on the scale of millions.
Ultimately, you have said it is a worldwide. How am I going to say this? You did say earlier in the show that essentially taking this picture has been done using a telescope, or many telescope arrays that have done a huge amount of maths to essentially act as the one Earth-sized telescope.
Yep.
So that's a lot of places across the Earth that have been doing a lot of work on this for a very long time. And so if they do successfully get an image, even if not for like the public's satisfaction of being like, "Oh hey, here's a cool picture," simply for the amount of people that would be excited by it, that they wouldn't shut up until it got on the news. I think
so too. It will definitely get in the news. For sure.
No, I mean, I really hope that people will do their part to spread the news. That's for sure.
I mean, I definitely will. In fact, if I get permission, I'm going no, that wouldn't do anything. I was going to put posters across my school, but we're on spring break.
Oh, so not allowed to put flyers across your school? What kind of school is that?
No, it's just that we're on spring break.
I'm gonna post the picture. There we go.
So it is going to be what's nice.
That's the 4 locations that they've been using to build this Earth-sized telescope: Antarctica, Chile, the West Coast, and Hawaii. I think that's a pretty cool.
I was hoping they.
Yeah, but this is I can see this is fake because the Earth is not flat on this picture.
Don't get me started.
Exactly.
I will be proving that it is round in the summer, so do not get me started.
Nice.
Since
Good
it
job.
is not flat,
Doing
I
the
may
good
need your
work.
help, but that's another topic.
you're lying because we all know that Earth is flat.
No, I mean, and in flat Earth, Antarctica doesn't exist. So everyone who went there
exactly.
is a liar.
So this image is a hoax. It's not real. It's
Yeah,
Photoshop.
I've only been to 2 of these
now,
places.
You see, now I know you're joking. Because you're very excited about this image. I have difficulty telling when people are joking about flat Earth because I hate them.
Yeah.
I'm a good
They
actor.
are dead serious. Hey, I'm happy to help you this summer to prove the Earth is round.
Thank you.
I will actually be in Hawaii in July, so if you want like a live measurement of something in Hawaii...
And so will I, because
he's tagging along.
For free.
Ripping off my free accommodation.
Yeah. I mean, the doctor here insisted that I would accompany her, because otherwise she wouldn't feel safe, and I reluctantly had to agree.
Yeah, that's exactly how it happened.
I am doing this for her own sake.
Right.
I don't really want to go to Hawaii.
And not for it's quite cheap.
Nah, I mean, I prefer the London weather. It's just my favorite.
Where are you guys currently in London?
Sorry?
Like in this moment, are you currently in London?
Yeah.
Yeah.
Right, okay.
Why?
Oh no,
I'm always in London.
No. No.
Well, no, we're not in London. Actually, we are in the cockpit of my ship.
According,
I am actually at waypoint 10.
The red comet. I am not even at the core.
Yeah, I'm at
exactly. My fake live. My side quest is happening in London. Yes.
According to London purists, I am north of the M25, so I'm not even a true Londoner. No one got that. It's okay.
No.
It's all right. Anyway, we are almost done. Was there something else I wanted to mention? Oh yeah, is it? So we're going to get a picture, right? A single picture, not multiple ones.
Currently one. And the resolution will probably not be that great. But first time. I mean, think of it. There was a first time where humanity got to see satellites around other planets, and people could see pictures of the moons of Jupiter for the first time. I mean, they may have heard they existed from like the newspapers of the 17th century saying Galileo finds moons, great. But there was a time when people saw them for the first time as a publicly available thing, and this will be the same magnitude as that, I think. A whole new kind of thing in the universe for people to see.
I know this isn't as popular as the other things, but there was also that, like, I can't remember the exact dimensions, but I remember it being like a 25 gigabyte file size. It was like a picture of Andromeda, and it was like you could zoom in and see like what a trillion stars looks like. That was...
I'm not surprised.
I love that thing.
It was amazing.
If my computer could figure out a way to successfully actually show it as a wallpaper, I would put it up. But because of the fact that it's just got a sheer, I mean the raw, uncompressed image, because compressing it completely ruins it. Like I was like 13 at the time, and I tried to post it to Instagram and saying, "Oh hey, this is so cool! Look at this!" And it ended up it was legitimately just like visible cubes.
Yeah, image compression is a bitch.
Yep.
Well, JPEG is
PNG.
PNG for the win.
I don't even well, again, I don't know much on the actual topic of this image, but I don't think it was actually a JPEG or a PNG. I think it was something well weird. It was, I don't know.
Fits.
A what?
It was a fits file.
I don't know. It was something suitable for. It was something. Obviously, it was a raw file, and so it couldn't have like JPEG or PNG. Or well, actually, no, it could have been a PNG. PNG is compressionless.
Well, it does have compression, but it's lossless.
It can be compressionless, but by default it's not. It could have been a non-compressed PNG.
Though.
Right, okay.
It's
Even if it's compressed,
lossless.
it just uses lossless compression like FLAC or maybe even Wave. I don't know.
It's not lossless enough to be used for science.
What?
No, it's
Is
not.
there-
We never use
Luckily,
PNGs.
I always use uncompressed PNG files.
Is there
those are
any
fine.
is there any image format that is completely uncompressed?
Yes,
Bitmaps?
that's FITS files. Bitmaps are one for cameras, and for astronomy they're called FITS files. And they're a bitch. Everyone hates them. It's a file format that's been unchanged since the 80s, and it's completely unfit for modern purposes.
And it hasn't.
But it's completely
updated?
lossless. It's perfect.
But it hasn't
Is
been
it-
updated in any way. Why?
No. And it's not even a unified format, so you can't even open it always in the same way. It's
Is
one
it-
of these things.
Is it annoying to use simply because of the fact that the file sizes would be huge, or is it annoying in the fact that nothing is actually programmed to
It's
properly
because
handle it?
it's because nothing is standard about it. You have to, it depends entirely where it comes from. And that's kind of fine, because each telescope records data in a different way. So you want to know in your data file also how the data was recorded and when, not just a value per pixel. You need a lot more information
But it
at
still
each
could
pixel.
be saved in some sort of metadata in the header or something like that. I don't
There
see
is
the
a
problem
header,
with that.
but different telescopes have different header keywords, because some of them use things like adaptive optics, some of them use segmented mirrors, all sorts of things. It has to be flexible, yet uncompressed.
In theory,
So
one could write a software that actually determines what method was used and stuff like that, and just can convert it, for example, into PNG to easier look at it.
Yeah, you can, but you really don't want to do that, because you lose a lot of the scientific information in the picture, which is more than just the number of photons and the color. So you have the amount of error, you have which pixels were contaminated by what and how much. It's like a many-dimensional image.
It would,
You can. There's one software everyone uses that kind of does that for you. It can figure out most FITS files, and that's it's called SAO DS9. Beautiful name.
Sort out online Deep Space Nine. I like it.
Yeah, it doesn't sound for that. I wish it stood for that.
Anyway, guys, we have reached the end of our allotted time, sadly. So, I believe we have answered all the questions. Remember that next week, same day, Wednesday evening, we will be here live to talk about this picture that we will be seeing. So make sure to be here.
At 1 p.m. in-game time.
Yeah, if Michael is organizing something like that, sadly I will not be able to participate.
But we will try to cover it live.
You know what? Message me if you do organize something. I'll try to get a live feed from our work. And you can see lots of nerdy astronomers.
I applied for online participation and I RSVP'd. So maybe we can do it on our own. Otherwise, I will contact you, of course.
Yeah, just let me know. I'm sure many of our PhD students will be glad to be live on the radio.
That sounds great. Okay, let's keep that in mind.
So, remember, put that right down in your calendar that we will be here. The picture will be commented live. So we will have our doctor explaining every single pixel of that photo and what it means.
Are you sure it's at 1 in-game time? Sorry to I thought it was at 4 p.m. UTC.
It's at 3 p.m. CEST, as far as I recall. Let me just scroll up a little. Where's the announcement?
Yeah, sorry to interrupt you, Nightfall.
No, it's fine.
Problem. It's an
Can
important
I just
issue.
say something?
Yeah.
Whoever did all of this changing the hour thing, please just
Stop.
Shut up.
Yeah, just stop. Please stop. Stop changing the hour. Everyone hates it.
I mean, ultimately, yeah, I enjoy an extra hours of sleep on one day of the year, but losing one on another and having to change my entire plans based around that, just shut up. I'm not.
Okay, I found the time. It's at 3 p.m. Central European Summertime. So that would make 1 p.m. in-game time.
Okay.
We're 2 hours ahead now.
Yeah, okay.
Are you sure?
I thought, okay, no, never mind. I believe you.
We have Central European Summertime right now, and it's 11:30 p.m. right now. So you should have 9:30 p.m.
Right, okay.
Yeah.
All right. Well, whatever. We will double
keep you
check on the
updated,
day.
guys.
Indeed. And anyway, whatever happens, we will still have Dangerous Cosmology in the evening. So
Yes.
in case you can't follow the real time thing, we will do what we're doing now and discuss everything about the picture in the evening.
Yes.
So this will be the end for tonight. Thank you all for tuning in. What? Why do you always stop things?
Sorry.
Go on.
Is it another joke?
Sorry. We may be having a last-minute question from
Where is it?
No, but it's ultimately up to him to post it right this second. So if you are listening, just ask, like immediately. 2.
Wait, there's a delay across the stream.
2. Oh yeah, there's a delay. I completely forgot.
Oh wait, actually Kenny had a question, but we're going to answer Kenny's question next time. Wait, we have actually. Okay, fine. Why? Look, you guys ruined my intro. Now you're ruining my outro. At this point, I'm just. I mean, do whatever you want. I mean, I don't care anymore. I mean, it's.
Sorry.
I'm trying to be all professional, and you guys ruin things.
Yeah, distant radio, ruining everything. That's our tagline.
Whatever.
Distant radio.
Okay, in the meantime, as Sereno is typing, is the exclusion zone that we see in the game something that we might see in real life? Can we bump into a black hole?
Lol, no.
It's a yellow ring around the black hole.
Can I read
the black hole will look like its event horizon is plastered with still images of everything that's ever fallen in. If time stops as things approach, wouldn't like take forever to leave and end up with still images over it? Yes, that's exactly what happens when things fall towards an event horizon. But as they get slower and slower falling onto the event horizon and appear to freeze on the surface, they also become more and more redshifted. So they change color, their light becomes a different wavelength. And so we cannot see them by normal means. They become redshifted out of practical wavelengths pretty quick. Especially with this picture that the Event Horizon Telescope is working on, they picked one specific frequency of light that corresponds to heated gas. So you would only see that specific temperature. Everything that fell in a long time ago is way too red by now. There you go.
Okay. Well, I hope that answered the question. I am not going to do the outro again because again I am annoyed by you all. So
please.
I will do the honors for you.
Sure, cool. So bye.
In Nightfall's name, thank you guys for listening, and don't forget next week 1 p.m. and of course 7:30 p.m. we will have our regular Dangerous Cosmology show about the Event Horizon Telescope and its newest findings. Yes. I hope that was okay.
Yeah, I guess.
You're annoyed. Okay. Anyway, thanks for listening, guys, and thanks for tuning in, and thanks for your questions, and of course, thank you, Nightfall, for hosting this show. Thank you, thank you, Dr. Sarah Bosman, for being here and answering our stupid questions. And of course, also thank you for being here, Selfish Pie.
Thank you.
For existing,
Yay.
for being 17. And
Yeah, I mean, we
knowledgeable.
every show needs a comic relief.
Oh,
So it's
my
good.
God,
that-
Gaffer, you're so rude.
No, it's because his jokes are so good that it's the comic relief, you know. That's
He wants to gather experience as a radio host, so being a comic relief is part of that.
yeah, exactly.
Also,
Yes.
bad jokes are a big part of being a scientist. So.
Being an
Practice.
idiot
Fair enough.
online is a part of what I want to do with my life.
Oh yes,
Great.
An honorable goal.
Also,
All right, guys.
yeah,
We
guys,
are out.
sorry,
We are out. See you next time, guys. Have a good night and see you in the black. This has been Distant Radio. Have fun and don't crash.
bye-bye.
Bye.